If not, I'm not sure how people raise their hands. And oh, my screen has gone blank here. Wait a minute. Okay, I seem to have two copies of our virtual world. Okay, good morning, everyone. And thank you for coming along to listen to me today. As you all know, I think you're not all PromeVR people, so maybe I should introduce myself. My name's David Swapp. I'm a senior research fellow in the Virtual Environments and Computer Graphics group at University College London. And I've been working in VR for quite some time there. I'm also part of the PromeVR2 project. And for those of you here who are not PromeVR2, this is a 15-partner EU project. And it is developing a VR platform that will allow the design of bespoke VR controllers. So for people who do not traditionally have access to VR systems, or for whom design of VR systems doesn't really work. So I'm not going to discuss the PromeVR2 systems per se, because I think that's going to get covered elsewhere in the PromeVR2 talks this week. But I'm hoping to do here is that by looking at the design evolution of today's standard controllers, we can gain some sort of insight into what it is that the human-centered design approach of PromeVR2 adds. So this talk is going to be a bit of a mixture of history, of descriptions of the supporting technologies for controllers, and the developments that have helped solve the variety of engineering problems that have been applied to controller design. And in particular, the real focus is that this seems to be the way this progress has largely been engineered and technological problems that have been solved, and this is how controller design has advanced. So first distinction I'm going to make is between head tracking and all the other forms of user control, because we'll go on to the next slide. Again. Okay. As we'll come to find out in this, so the ability to track in 3D is fundamental to VR control mechanisms. But what distinguishes head tracking from all the other tracking is that this is what provides us with control over both our visual and our acoustic perspective virtual environment. So if we don't have head tracking, we lose this huge immersive component of the system to the extent that we can't really call it virtual reality anymore. So we would expect our view to change appropriately as we look around the scene, and even small head movements provide parallax cues that tell us about the 3D layout of the virtual world. So while head tracking is of paramount importance, in this talk I'm not really going to be focusing so much on head tracking. I'm going to be focusing on other forms of control within VR, the forms of control that allow us to interact with and manipulate the 3D environment. So primarily handheld controllers, but I'm also going to look at alternative forms of control and potentially richer forms of control. Another distinction that I'm going to make is between magical and natural interfaces. You can see I'm trying to pare this down a bit so that we have a narrow enough scope to fit into one talk. So again, I'm waiting for this slide to advance. It's just not moving forward.
You want to go to the next slide, David?
I'm trying to. Is there anything you could do to intervene? If it's
have you tried
the...
can you refresh it? Maybe on the top right corner, besides the zoom button, there's a refresh button.
Okay. Try that again.
There
we go.
Yeah.
Okay. So, what was I saying? Yeah, so not going to focus on head tracking, going to focus more on manual control. And I'm also going to make this distinction between magical and natural interfaces. So what do I mean by magical interfaces? I mean the kind of things that give you superhuman capabilities. So extended reach, for example, the GoGo interface. So this is an interface that extends your virtual limb exponentially to the extension of your actual limb. So if you have your hand close to your body, it's in a normal place, but if you reach out 5 meters, 10 meters, whatever. Flying is not a natural interface unless you're in a flight simulator. So if you have some sort of vehicle metaphor going on, I guess that's okay. Teleportation, even using a joystick to navigate around in VR can be considered a magical technique. It's certainly not naturalistic, but again, as I say, vehicle metaphors can occupy a slightly grey area here. And the reason I'm going to leave aside these types of interface is that well, I mean, these types of control mechanisms certainly have a place in VR, and the acceptability of any particular interface design is always going to have some dependence on the context of the VR simulation. So, for example, a joystick might be perfectly appropriate for a flight simulator. But the reason I'm not going to discuss these types of interaction is that although I'm not going to talk directly about the PromeVR2 controller, I do want to talk about controllers within the context of using actions that can be transferred to the real world. So I'm not going to talk about the PromeVR controller itself, but want to talk about realistic forms of manual control. So what should the ideal controller be able to do? Again, I'm trying to get the slide to advance. Okay, so in the context of VR and naturalistic interactions, our ideal controller should support everything that we can do with our bodies in the real world. We should be able to walk or run, reaching and grasping, throwing, and a whole range of other actions, catching, writing, typing, fine motor skills. But to achieve all this would require real-time measurement, not only of the location and posture of our body, also the representation of forces across the surfaces of our body at a very fine resolution. So, and the ideal tracking system would not just have to do this, but it would have to do it with accuracy and with low latency. Now, the requirement for latency is maybe more critical for head tracking for reasons I'm not going to go into. But even then, the acceptable limits for hand tracking are still quite low in terms of quite low latency. And in some types of interaction, actually, the tolerance for latency are even less than they are for head tracking. So we're still a long way from this goal, but what we do have in 2021 is a range of different technologies and devices, and each of these fulfills some subset of the functions of this ideal controller. So where do we begin with VR controller design? And how have we reached the types of device design that we have today? Really, the controllers we have now trace their origins to the designs of 2D tracking devices, such as the trackball and the computer mouse. So trackballs have been around since the 1940s. They used to use them for plotting coordinates on military maps. But this is the design that inspired the computer mouse. The computer mouse is basically a trackball turned on its back. So you don't manipulate the ball, you just roll it across your desk or your table. And the device typically has 2 or 3 buttons for some selection or other interaction. Now, the design of desktop mice has evolved. One we can see there is, I think, from early 1980s. It's evolved since then, along with graphical user interfaces, but the design is clearly recognizable to us today as a mouse. Now, the 2D mouse relies on a mechanical connection. It's mechanically connected to whatever surface we put it on. And this maps the movements of the mouse to virtual movements of a cursor on a computer screen. For 3D tracking, there are mechanical tracking solutions. In fact, later on, I will mention some mechanical tracking solutions. So they're certainly possible and necessary in haptic systems. But mechanical tracking it's practically restrictive. So if you think about the mechanical linkages and connections, if you've got more than one tracker, they're just going to get in each other's way, and the whole system is going to be very cumbersome and not very usable. So instead, there are a few other good candidate technologies for 3D tracking. And all of these are used sometimes in combination in the VR controllers that we see around us today. So magnetic tracking. So the idea of tracking objects by measuring their magnetic fields goes back, goes back decades. The first electromagnetic tracking systems for 6 degree of freedom, position, and orientation tracking came about in the 1970s. And the technology is quite simple. It relies on creating 3 orthogonally oriented magnetic pulses via transmitter, and then measuring the response to these via the current induced in 3 orthogonally oriented coils mounted in a sensor. So if you imagine the diagram in the middle here is one magnetic field in one orientation, you place another magnet in there, or sorry, you place a coil in there, and this magnetic pulse will induce a current in it. And current will be dependent on the orientation of the coil relative to the magnetic pulse and the distance from it. So with 3 coils and 3 orthogonal magnetic fields, you get 9 measurements, and this data is enough to yield very accurate 6 degree of position and orientation of a sensor. Magnetic tracking has some advantages. They're the ones in green. It doesn't require a line of sight. So a lot of tracking solutions do require a line of sight. It's not always convenient. What if the tracker disappears under your desk? What it also does is it provides measures of absolute position and orientation relative to the transmitter. Again, you'll see some other solutions don't do this. But the sensors have to be tethered because they're producing a current. So unless you're going to have the control system with the sensor, you have to have it connected by a wire to your control box. And also, ideally, it should all be set up in a metal-free environment because any metal in the environment distorts the magnetic field produced by the transmitter. And obviously, if you're in an environment with computers and other electronics, it's very hard to be free of metal. Now you can calibrate to account for the distortion, but you still compromise the accuracy because you've distorted the magnetic field. So it's a compromise, but it's something that you can work around. Next thing to look at, inertial tracking. So again, this takes an idea that's been around for a long time. So on the left is the gyroscope system from Apollo 11, which is huge and very heavy. But in the 1990s, it became possible to fabricate similar kind of device with microelectronics. So microelectronic accelerometers and gyroscopes could fit into one of these devices on the left. Now this is not even to scale. So compared to the gyroscopes on the left, this IMU is much, much smaller. That's in a block about 1.5 centimeters across. So on the right is something called an IMU, inertial measurement unit. Now, these also have the advantage of not requiring a line of sight. They're not affected by calibration problems, magnetic fields. They do have is drift. So they don't measure absolute position or orientation with respect to some reference frame. They measure linear acceleration and they measure rotational velocity. And you can derive absolute position and rotation just by accumulating all the measurements. But if there's any slight inaccuracies, even just rounding errors creep in, these will accumulate, and over seconds, minutes, they get bigger and bigger. So over time, the measured position and orientation will drift away from the real position. But as we'll come to see, there are workarounds for this. Another way of tracking, still used, is acoustic tracking. So here you use small loudspeakers and you mount these on a static reference frame. And you also have small microphones mounted on whatever it is you want to track. So this is your controller or your head tracker. The small microphones go on there and they will be spatially separated. So the loudspeakers will emit ultrasonic pulses, and these are detected by each of the microphones. And you just use time of flight measurements, you know the speed of sound, between each loudspeaker and each microphone, and you can triangulate position and orientation very, very accurately. Now in practice, most systems will have a lot more than 3 loudspeakers. They will just have a whole array across the ceiling, and they will use the 3 nearest ones to produce the most accurate result. So the system is very accurate, measures absolute position and orientation. It's unaffected by magnetic fields, mostly unaffected by background noise. If there's lots of ultrasound in the background, then obviously it will stop working. Fortunately, most ambient noise does not contain a lot of ultrasound. The main disadvantage of these systems is that to some extent they require a line of sight. Not necessarily, sound's quite good at bending around objects in the way, but you could potentially block it completely. They have a relatively low update rate, and this is entirely due to reverberation. So if you have long reverberation in your environment, then it has to wait before it can make the next reading. It's still fractions of a second, but still we want something more like milliseconds and not seconds. The ones I'm putting in orange are not really showstopper. So acoustic tracking is affected by the weather, speed of sound is affected by temperature, and again, wind wreaks havoc with sound waves. But normally, if you're in a VR lab, you're in a controlled environment with controlled temperature, and you shouldn't have any drafts coming in. Now, what you probably noticed from these slides is that these tracking systems have different strengths. and you can combine these to create more robust systems. So, for example, inertial tracking is relatively inexpensive, it's light, it doesn't weigh much, it's compact, it's low latency, and high update. The shortcoming of it is that it doesn't measure absolute position, so it drifts and becomes inaccurate. So this makes inertial tracking a good candidate to combine with something that's more accurate, but maybe higher latency, not such a high update rate. Now, what tends to dominate now are optical systems, or at least this is what dominates the commodity head-mounted displays that we have now. So optical tracking in itself, it offers a vast range of technological solutions. So I'm not going to cover all of these in detail. I'll cover the main solutions that are actually used with contemporary VR systems. First distinction is between inside out and outside in systems. So inside out systems place the sensors on the track device. So for example, the ultrasonic system described earlier, that's inside out because the sensors, the microphones are on the track device, and the emitters, the ultrasonic emitters, the little loudspeakers, they're in the array around the track volume. For outside-in systems, it's the other way around. The sensors are placed around the track volume, and they detect signals that are produced by the track device. Now, an outside-in optical tracking system is going to place cameras around the track volume, and these will detect light that's emitted or reflected by markers on the tracked object. Outside-in systems are typically used for capture of many tracking points. So, for example, full body motion capture. But they have also been applied to head-mounted displays and hand controller configurations. Optical systems are very dependent on line of sight. You get something in the way, it blocks the light, they stop working. So there's some redundancy built into outside-in systems, and an array of many cameras to ensure that there's enough of them to have a view of each marker to compute position. So passive systems will use small retroreflective spheres to reflect controlled light back to the cameras, but the system has to keep track of which marker is which. So you get problems with marker swap. The system will get 2 markers mixed up or 3 markers mixed up. And this happens when somebody wearing a motion capture suit makes a rapid movement that maybe changes the array of cameras that are seeing each marker. And with this, you'll get odd results in your motion capture. Active marker systems don't have this problem. Each marker will emit a unique optical code, so there's no possibility of the system getting markers mixed up. Now, inside-out optical tracking systems, they place the cameras on the trackers, and these will detect optical features in the environment. So some systems will use structured light, so I'm thinking the Vive Lighthouse system, and thus they need a line of sight to each of the lighthouses. And then you have systems like the Oculus Quest, which use built-in cameras to scan and build up a 3D map of the surrounding environment. Now, this obviates the need for external devices, so there's no line of sight requirement, and there's less setup as well. But the tracking quality is still dependent on having a feature-rich environment. So Oculus Quest won't work very well if the cameras can't find features to recognize and track themselves against. So what are the main types of tracking that support VR controllers? So these are the main types of tracking that support VR controllers. But what about the controllers themselves? So the first one I'm going to show you is a controller from 1990. That's the slide. Here we go. So this is a Logitech 3D mouse. I just got this out the other day and it still works. Now, this uses ultrasonic tracking. So the triangular frame that it's sitting in has 3 speakers mounted in the frame, and the mouse itself has 3 small microphones. And both these elements are tethered to that control box you see on the left. Now, in terms of design, you can see this is pretty much borrowed directly from 2D mouse design. It's got 3 buttons for interaction, but it looks remarkably similar to a 2D mouse. So you hold it in a similar way, and the interaction is broadly the same. Now, fast forwarding quite a bit. So this is kind of looking over the next 25 years after that. You tend to first thing you notice is that the shape and the topology is still recognizable. So there's the addition of a joystick control for navigation. For the PlayStation controller in the middle, the joystick was actually part of a separate device. But you have some buttons across the top, and in all cases, you've got a trigger underneath. So quickly moving through. So the InterSense system, they went through various iterations in the early 2000s. That uses hybrid tracking. It uses inertial combined with ultrasonic tracking. So it's inside-out tracking because the microphones are in the device, and additionally it has inertial unit inside the tracker. So the inertial unit has high update rates and low latency, but drifts, whereas the ultrasonic system is highly accurate, measures absolute position and orientation at a much lower update rate. But if you combine both of these, then the inertial system will start to drift, but not for very long, not very long enough for you to notice that it's drifting before it gets corrected by the latency ultrasonic system. PlayStation Move, this similarly, it combines inertial sensors with an absolute position system, but the absolute position system here is optical. It's a single camera, captures the light from these spherical lights on the top of the controller. So it's really designed primarily as a gestural interface. It doesn't have the same accuracy requirements as other VR controllers. It does have some nice, clever features. So, for example, the spherical lights on the top change color. They detect color. The camera detects the color of the background you're in and changes the color of the lights to make them stand out more against the background. And lastly, on the right, this is ART fly stick. So this is very similar to the InterSense system, 3 buttons and a trigger and a joystick, but it relies purely on optical tracking. So it's similar to motion capture systems, has a pattern of retroreflective markers that are unique to the controller, and so the ART controller itself is, you see the camera on the left, is surrounded by near infrared LEDs. They bathe the tracking volume in near infrared light. So even in low level visible light, the tracking continues to work. In this case, we've got 6 cameras tracking a 3x3x2 volume. You could normally do this with fewer cameras, but to get into the corner of closed volumes, you require a little bit more. But you have a very accurate system with low latency. So moving on to Vive controllers. So here you see the design has evolved slightly. So we've got a similar shape to before, and we still have a trigger button on the underside. But the main interface feature on the upper side is a thumb-controlled trackpad, which you can't see very well on this, but if you're familiar with these devices, you have a large trackpad in the front. You still have 2 buttons on the front, but these are smaller and they are more driven towards system or application menus rather than selection. There's also a small grip button on the side. So this is the first controller you see this on. For the Vive controllers, it's quite small, tended not to get used very much by developers. Quite a lot of people who have these controllers are not completely aware that they have a grip button on the side. So these use inside-out tracking. They've got 24 internal sensors detecting structured light from the base stations. So the base stations are sending a pattern of light out. There's LEDs and a spinning laser beam, and the sensors inside detect the time difference between these to work out their position. Moving on, we have the Oculus Touch controllers. Now, again, there's a bit of design evolution here. They use a very different tracking system. Both of these controllers use outside-in tracking. They have an external sensor that's not on the device. Then this detects a pattern of LEDs that's embedded in the controllers. For the first generation, the one on the left, the sensor was a separate camera that you had to buy and you would put on your desk, and it detected both the headset and the controller. In the second generation, you see on the right, this is the one that's used with the Oculus Quest. The external sensor is in the headset itself. So the headset itself is the sensor for the controllers. So what this means in practice is that they both have lower power consumption than their inside-out trackers we've seen before. So they weigh a lot less than a Vive controller. So these weigh not quite half what a Vive controller is, but getting towards that. Now, they both, looking at these, they both have a very similar layout. They've got a joystick, they've got 3 buttons on the front face, they've got a side grip button that's better than on the Vive, and they have a trigger. The main difference in appearance is the movement of the ring housing the LEDs to the top of the controller. But this is just another technologically led design decision, because what it does is make the ring of LEDs more visible to a head-mounted display, whereas the other one before was designed to be visible to a camera that's sitting on a desk further away. Onto a different type of controller. Not all our controllers are controller-shaped. Data gloves, they seem like a very naturalistic way of interacting. So what they do is they sense our hand posture, so they're ideal for gestural interfaces. But what they lack is any controller inputs. Now you can manifest controller inputs virtually, but then you're not going to get the passive haptics, the feel of pushing buttons or pushing down the controller. These first appeared in the 1970s, so the early versions of these used optical flex that would sense the curvature of an optical fiber, because these would be designed to transmit less light when they were bent, and this would be converted to an electrical signal. Gloves that I'm showing you here are from Manus VR. We bought a pair of these a couple of years ago at UCL, and these have thin bend sensors in each finger, and these sensors are a kind of coated substrate. It's basically a piece of plastic with a substrate. The electrical conductivity varies as it bends, and the can, if you want to have degree of freedom hand tracking, you can mount a Vive puck onto the gloves. They have a mounting position for that if you want to augment beyond just having hand posture. Now, this is saying these completely lack any kind of touch feedback, not even the passive haptics of a commodity controller. So something we can do here is look at force feedback controllers. So these are designed to mimic the weight of an object that you pick up, or the solidity of a wall or a solid surface. Now, Oculus and Vive controllers, you will see they offer haptic feedback, but this is in the form of vibration. This is something that's sometimes referred to as a form of pseudo haptics. It's not really an attempt to mimic real world forces. Phantom Omni on the left is a mechanical motor-driven controller capable of presenting force in 6 degrees of freedom, so linear and torque forces. And the Haption Virtuos on the right, this works in a similar way, but has much larger motors and supports a more human-sized range of motion, and obviously bigger forces, so up to sort of 10 newtons peak. This one you see here is mounted upside down. It's sometimes a convenient way to mount it. So what the kind of things you get from the Phantom Omni and the Haption Virtuos, the sensation you get is well, the forces are applied to a stylus, the end of the device, the end of the mechanical linkage. So the impression you get is much like you would get if you were interacting with the world holding a pen or a screwdriver. And often this is referred to as tool-based haptics. And this is not really a criticism. Tool-based haptics is often a very valid use of haptic systems. It's great for tool-based training, for example, or surgical training. Now, an alternative to this kind of tool-based haptics is a worn interface. So what you see here is an exoskeleton interface. This is a device that was loaned to UCL about 15 years ago for a museum project. And the interface, although it's very heavy, it supports itself. So it's ground-based, and the motors will apply in a neutral position. They will apply enough force to make the whole armature weightless. So the only forces you experience in the unit are those that are simulated by the VR experience. So in this case, it was walking around a museum and being able to touch the statues.